Today we're going to talk about integrating unequally spaced data. Okay? And what I mean by that is when we've been performing Trapezoid Rule and Simpson's 1/3 rule, we actually had a function to work with, and so we could use equal spacing between our x values. But notice here, the spacing is actually pretty similar throughout this, but we also have this little gap here where the spacing isn't equal. Okay. This one wouldn't probably be a big deal to work with, just for the fact that the spacing is pretty consistent. But the question is, well, what do we do when we have data that is unequally spaced? Okay. This is actually a data set that we worked with in homework 6. Let's go ahead and run it and see what it looks like. So our goal here today is just to approximate the area under this. Okay. And we can do this two ways. One is we could create a trapezoidal rule function that just can work with unequally spaced data. Okay. It won't be quite as efficient. Or we could fit this with a curve and then use our trapezoidal rule function that works for equally spaced data. Okay. Either one would work fine. Okay. Let's go ahead and switch to OneNote and see what the trapezoid rule is going to look like when we have unequally spaced data. Okay. So here it is. And this actually looks exactly like what we had started with in the derivation for the trapezoid rule. It was just that since all these h's were the same previously, we were able to combine all of the middle terms. There would have been an extra f2 to combine here, an extra one of these to combine here. Okay. Right? All those middle terms would have been taken care of by just computing them once and multiplying by 2. Okay. However, we're going to have to leave it in this form right here, which isn't a big deal. This is not a big deal. Okay. And in fact, our code's actually going to look a little bit more simplistic because of this. Okay. Let's go ahead and switch back to MATLAB. So we have a function here, and we're going to call it trap UNEQ for unequal. Okay. Our output will be, of course, the approximation for the integral, which we'll use capital I for that. But we only have two inputs this time. We just have our data for x and our data for y. These should have the same number of elements in them. Okay. Let's see. Let's go ahead and start working down here. So if nargen is less than 2, okay, right, then we have an issue. We need both the x and the y data set. So if nargen is less than 2, let's say there is an error, and we need at least 2 input arguments. Okay. And we'll end it. And now we're going to use a function that we have yet to use before. And I want us to kind of see how it works maybe down here. I'm going to create us a little vector. Okay, so there it is. And then I'm going to have us compute diff of x. And let me just scoot this up. See if you can figure out what it's done. All right, let's go ahead and see. So if you were to do 1 minus 5, that'd give you 4. Okay. If you were to do 5 minus 8, that'd give you 3. Okay. 8 minus 4. Oh, I'm subtracting these in the wrong order here. It did 5 minus 1, 8 minus 5, 4 minus 8, 3 minus 4. And that's how it got these 4 numbers down here. Okay. All right. Now, the thing that's going to be really important here to note is that when we are increasing from one x to the next, this difference is positive. But when we're decreasing from one x to the next, the difference here is negative. Okay? And the reason I'm pointing this out is we need our x data to be in order. Okay? So let me give you an example. Right? We go from smallest to biggest here. We want to go left to right on our number line. Okay? Otherwise, that's going to mess with our formula that we're going to have that's going to deal with the spacing. Okay? And I'm going to go ahead and enter this one now, and we'll use diff on this, and we should see that all of these differences are positive. Okay? Good, and they are. And we're going to need this here. So we're going to say if, and we have this nice little function here, any. I'll explain that in a second. We're going to look at the difference of those x values. And so what this is saying is if any of these differences are less than 0, okay, we're going to report an error. X is not monotonically ascending. Next thing we're going to need is we're going to need the length of our vector x, because that's going to determine the number of subintervals we have. Right? If we have n data points, we're going to have n minus 1 subintervals. Let's go ahead and get that in here. So n is equal to the length of x. And then if, right, we said x and y must be the same length here. So if the length of y, let me fix that, is not equal to the length of x, which we said is n, then we'd like to report an error. Okay, and how about for this one? X and y must be the same, or be the same length. All right, and now we can finally get into creating that sum that we had in OneNote. Let me pull it up again real quick. So here it is. It's just the h is just the difference in these x values. Okay. And our sum is just you add the two consecutive function values and divide by 2. That's the trapezoidal rule. Okay. That's how you find the area of a trapezoid. Okay. So we'll start off with our sum being 0. But as soon as we get our for loop started, that'll change. So for k equals 1 to n minus 1, right? That's how many subintervals we're going to have. S is equal to s. So this is saying s is now equal to the previous s plus, and now we need our formula. Okay? So the first thing I'm going to put in here is the h, the change in x. So that should be x of, and actually I'm going to leave that blank for a second, minus x of something. Okay, so this is where the bigger one's going to go, and here's where the smaller one will go. And let's think about the first element in x. What would that look like? Well, that'd be x of 1. Okay, so if we're starting with 1, then I want a k here. That way, the very first subtraction here is going to be x of 2 minus x of 1. That's what we want to happen. So I'm going to put in a k plus 1 there. Okay, so there's h. Next, we need our little formula. We need to sum the two consecutive y values and divide by 2. So this is going to look like y of, and let's just take a quick peek at it. So we're going to start with f of x sub 0 plus f of x sub 1. Now, remember, we can't start the index of a vector with x or with 0, right? It starts at 1. So this is really going to be for the first iteration. This is going to be y1 plus y2, and then y2 plus y3. But let's just keep that in mind, y1 plus y2 for the first one. So we just want y of k plus y of k plus 1. And after that, we want to divide that by 2. And we can end this, and then I equals s. Okay. And let's go ahead and save, and let's test it out. And I like to always check and make sure that I suppressed everything before I use the function. And there's not much to check there. Everything looks suppressed. Let's go into, yeah, there it is. There's our data. Let's go ahead and compute this integral. So we have trap unequal, and we just need to put in t and p. Okay, and I'm getting an answer here of 19.5. Okay. Now, you might be wondering, is there a way that we can kind of maybe check our work or think about this maybe in another way? And the answer is yes, we can. Is what we could do, and actually I'll hit run again. We could fit a curve to this data, and then we could use our trap function, okay, instead of trap unequal. Let's go ahead and do that. Okay, I want to make you recall what the function's supposed to look like that'll fit this data. All right, and I've just commented it in here. It is this right here. Okay. And if you remember, this was actually something that was pretty quick to perform polynomial, or not polynomial, to perform linear regression on. Okay. And the idea was we thought about our basis vectors. Okay. And our basis vectors all look something like this. In other words, P, for varying A, B's, and C's, that's just one way of saying we're taking linear combinations of e to the minus 1.5t, e to the minus 0.3t, and e to the minus 0.05t. This is the basis for functions that look like this. Okay. So next, we'd create that little matrix. I'm just going to call it M. That consists of us just plugging t into these basis vectors. Okay. And that's why I have these written, by the way, as column vectors. That's why I've transposed them, is I want the first column, not the first row, to be e to the minus 1.5 times all those t values. I'm just going to put that right there, and that'll do the trick for the first column. And actually, I'm just going to copy the next two all at once here. There we go. That's going to create 3 column vectors, or a matrix with 3 columns. Okay. And let's keep going. Okay. The next thing that we would like to do is actually compute the coefficients A, B, and C. I'm going to call them just coefs. So our coefficients, this is going to be equal to M transpose times M backslash M transpose times P. Okay. And the thing that we can do next is we can actually write the function that would result from this. Okay. Let's maybe call it, how about f? And I suppose I'm gonna leave the variable here as x. That way we don't have any conflict between all these t's in here. And actually, I'm gonna just copy and paste this, and we'll make a few edits to it, but this is mostly what we need. Rather than a, we'll have coefs of 1. Rather than b, we'll have coefs of 2. And rather than c, we will have coefs of 3. And rather than t, I'm just going to make these x's. Okay. And if we just want to double check our work here, we could put a little hold on here. And by double check our work right now, I'm talking about double checking that this actually fit our data. We could use fplot, our function, and then the interval we want, which is 0.5 to 9. Okay, and the only other thing I want to think about here for a second is, do I need to put any extra dots in this function? And it looks like the answer is no. So let's go ahead and run. Okay, seems to fit our data great. Let's now use, we can really use anything we want here. We could use the integral function, Simpson's 1/3 rule, or our trapezoid rule function. Okay. Let's use the integral. So I'm going to maybe say, that's our answer that's going to result from our trap function we just used. And here, let's just say int for integral. And right, we want our function. Okay. What else do we need? Well, with the trap unequal function, it is really obvious where we're going to start and end our integral, because we're given this data as is. We know we're going to start at 0.5. We know we're going to end at 9. Okay. However, the integral function, this is not obvious because you're plugging just the function into it. So we need those limits of integration. We want to say 0.5 to 9. And if we choose to, actually, this is it. This is it right here. Let's go ahead and run. All right, and we have pretty similar results between the two, so we can be, pretty happy with our trap unequal function.